There we go, I think this is working. So, I'm here today to talk to you about the decline of the Synapsida across the Permo-Triassic extinction and early Mesozoic, and looking at that using mandibular morphometrics. So, synapsids are a highly successful group of amniotes. We are all synapsids, Mammalia belongs within that clade, and not only are they successful today, but they were also successful during the late Paleozoic. So after emerging in the Carboniferous period, they experienced two great radiations in the Permian. One in the early Permian with a radiation of pelycosols, giving rise to such sail-backed forms as Dimetrodon, as seen over here. And then we also have a radiation of therapsids in the late Permian. This is when we start to see the synapsids beginning to look less like reptiles and a bit more like mammals, which we'll see as we go on. So they were harshly hit, like most life during the end Permian extinction, and despite that, they recovered quite well, according to diversity studies, in the early Triassic. However, it was the diapsidarchosaurs and not our synapsids that would go on to dominate the late Triassic and ultimately the Mesozoic. So why did that happen? Well, that's what we wanted to look at, and we decided to investigate that using mandibular morphometrics. So, why use morphometrics? Well, it is the study of form, and the quantitative study of form. And form can tell us many things. So, principally function, but also perhaps the ontogeny of the organism, and maybe even clues to its phylogeny. So, it's highly informative to us as paleontologists. Now, geometric morphometrics allows us to quantify form by essentially taking landmarks off our structures and giving them Cartesian coordinates so we can plot them in space. And that's essentially what we did here with mandibles. So you can have a display that as disparity in discrete data, so disparity trends through time, or we can plot it more sort of visually as morphospace. So why mandibles? Well, they're highly functional parts of the vertebrate anatomy. After all, they are primarily responsible for the ingestion and mastication of foodstuffs, and therefore highly relevant to studies of trophic ecology, which is an important factor in studying any organism's sort of ecology, really. So, we created an updated list of synapsid taxa, including mammals from Benton's 2013 paper on the diversity of tetrapods. And going through this list one by one, I searched out usable images of mandibles that were relatively complete, undeformed, and hopefully adults. There are some, like how Armin said, where there's no data if it's a juvenile or an adult, but we just went with the largest one again. So, landmarking was carried out using TPS software. We also carried out the Krusty's alignment, which removed the orientation and size of our images so that we were just focusing on shape. Now, we also carried out the principal components analysis, which identified the principal axes of variation, and these were the axes that we would then use in subsequent analysis of disparity and morphospace through time. So, here is a few of our mandibles with the landmarking regime imposed over it. So as you can see here, we have 4 fixed landmarks, and then we have 4 curves of semi-landmarks. So this was a conscious choice to use semi-landmarks as well, because we felt that fixed landmarks alone were unable to fully capture the variety of different forms here. I mean, one thing that was really quite difficult was that the cynodonts undergo quite a major sort of stage of mandibular reorganization of the points of articulation. So you see a change from a more reptilian jaw joint to something more like a modern mammal. So the semi-landmarks allow us to capture the variety of forms here. So we have a cynodont up here, we've got a dicynodont and a nomodont here, and then we have a therocephalian. So I think you can all agree with me that these are quite diverse sort of mandibles, and yeah. So we were able to capture that pretty well, we thought. And these are our main synapsid clades that are represented in this study. So we do have a couple of eupelycosaurs down here. So remember, that's the Dimetrodon sort of clade there. And then as you go forward through time, we get the evolution of the therapsids, we get the biomarsupials over here, which are the most basal members, and they're generally characterized as small, lightweight predators. Then we have the Dinocephalians, a really diverse group that includes both herbivorous and carnivorous forms. Really strange things there. And then we get the Neotherapsids, so a nomodont, dicynodont, very, very widespread and really successful group of synapsids. And then we have our saber-toothed Gorgonopsians up here, Therocephalians, and right up here at the top, Cynodonts. And you can't see it on here, but there's a little arrow that shows where the mammals would appear. So moving on, this is the first output of data, not very informative, I know, but don't worry, it gets better. So here we have our thin plate splines representing the different areas of this plot. So as you can see, PC, principal component axis 2 represents the presence or absence of the coronal process, and then PC1 represents the thickening and shortening of the dentary. And right here in the centre is sort of like our mean synapsid mandible. So showing you where our guys cluster really, we have the eupellicosaurs sort of clustering right here, just off the centre, and we define that area as the sort of primitive synapsid jaw. And then we have our marsupials appearing up here on the right, and then we have Dinocephalians down here and sort of taking up a small space just across this axis here. And Nomodonts, interestingly enough, cluster away from everything else pretty much, right down here. This is all them. So that's quite a good idea that they are very distinct. So we can capture that in our morphospace. Now as we move on, we have the Gorgonopsians again clustering in the same space more or less as the Dinocephalians, but however they occupy a much wider space across pretty much PC2. And then right at the top here, we've got the Cynodonts and Therocephalians. And just over here is where we would get modern mammals appearing. So just to recap here what I've said, giving you an idea of what these different areas represent. So while this is not really that informative through time, this one is. So this is the same plot, broken down into time slices. We're going from the Wordian in the late Permian all the way to the Pliensbachian in the early Jurassic, and as you see, we're color-coded by clade. So moving forward, we've got our radiation in the late Permian of Therapsids, which can again be broken down into two phases. We've got Dinocephalians radiated here, and then the radiation of Neotherapsids. However, all this is pretty much wiped out at the Permo-Triassic extinction, where we see the extinction of the Gorgonopsians as well as the Biomarsupians, and pretty much leaves only the Theriodonts and the Anomodonts as the only surviving synapsid taxa. So as we go through, we can see in the Initian that this is the peak point of morphospace occupation following the Permian extinction. And as you can see, the Therocephalians are pretty much on their way out. There are only two members here in our study, but we've got quite good coverage of them at this point. And the Anomodonts have managed to cover some disparity, but as you can see, it's a shadow of its former self. So as we keep going through, we see the extinction of the last Therocephalians, and we see the decline of our Dicynodonts. And also, Cynodonts seem to show sort of contraction and expansion of morphospace. So our results seem to tally with additional studies of morphospace and disparity, such as Reuter's 2013 papers on Cynodonts and Anomodonts. So we're pretty confident of what we've got here. However, when we looked at this, we were trying to sort of figure out what's going on here in relation to the archosaurs and their rise. And looking at this disparity data from Brisat et al. 2010, which looks at general disparity as opposed to particular disparity, by the way, don't worry, that's on its way. Not in this talk, but in another one at some point. And we've got the key moments of, the key times of archosaur diversification. So they begin to diversify here in the Initian, really, or around this time, and then we see a rapid increase in disparity just in the Carnian to the Norian, and then in the Norian and the Retian we see peak archosaur diversity and disparity. So at this level, you can't really determine much in terms of a relationship. So we're going to break this down again into geographic regions. So we've got northern Pangaea, so mainly up here in the European and sort of North American areas. We've got the equatorial regions, such as Brazil and parts of West Africa. And then, of course, we've got South Africa for our southern regions, sort of Caribbean Basin. And if you look at it now, broken down in time, you can see quite a different pattern between these regions. So much of the synapsid recovery post-Permian extinction is in the south and equatorial regions. There's nothing going on in the north, pretty much. You've only got a couple of Lystrosaurus there, and then Cynodonts started to come in until sort of like the Norian. And now looking at this in terms of the archosaurs, just on our own occurrence data, we find that archosaurs are mainly situated in the north following the Permian, and that is where they start to diversify. And as they move south across Pangaea, we find that the synapsid recovery goes into, it slows down and ultimately goes into reverse. And although we can't be conclusive in that at the moment, it will be interesting to test it quantitatively once we get the archosaur manual data. So this is sort of where we're drawing our conclusion now. Because it's always difficult to look at competition in deep time because the time scales are just, you can't really look at it properly on the scale that we look at it today. So it's always you've got to take this with a pinch of salt at the moment. But it is interesting enough to see this. So here's just a disparity plots for our different regions and also for just global in black here. And if we look with the archosaur data superimposed over it, we see that as archosaurs are prevalent in the north, in the northern regions, the synaptic disparity is pretty much gone and drops off. There's the one point where they seem to have any possible data. And then as they move south across Pangaea, and we see major increases in archosaur disparity, first in the Keratasians and then in the Ava-Metatarsa, we see that synapsid diversity and disparity drops off in the late Triassic. And ultimately this here is actually a signal of the fact that there's only one dicynodont left and a few cynodonts, so that's an artifact of the data. But if we follow the trend, it just shows that the synapsids really had a hard time of it once archosaurs. So where next for this? Well, we hope to expand the synapsid data set. We had roughly around 200 taxa included in this study, but there were quite a few more where we saw there were usable mandibles, but unfortunately we couldn't get access to them. And of course we are carrying out a parallel study on the archosaurs, and we will be testing for quantitative relationships between them in the near future. And of course, one other thing to bear in mind is that, yeah, we're seeing shape change, but does this really relate to changing in function? Does this actually relate to a change in the diets, perhaps? Well, we'd like to think so, seeing as, if I were to go back a moment, we can see that there's a clear break between areas of, just over here, for example, clear areas between herbivory and then carnivory in the sort of top right. And we can see trends such as in the cynodonts, where you find in the middle Triassic cynognathians going towards herbivory and omnivory, and then later in the end Triassic you find the Probaionathians going for the same thing, and we can see that represented in our data. So, thank you very much. Any questions?